The theory of relativity. Perhaps no other idea in science evokes the sense of strangeness and abstraction of modern physics. Perhaps no other idea has been more misunderstood or more misrepresented. But at its root, relativity is a relatively simple concept. Its great underlying principle is that the laws of nature are independent of the observer's frame of reference. In other words, every observer anywhere in the world, anywhere in the universe, sees the exact same laws of nature. In this 16th lecture, I want to accomplish 4 goals. First, I'm going to look at the philosophical implications of the principle of relativity. Then we're going to calculate the magnitude of relativistic effects using Einstein's theory of special relativity. In the process, I want to underscore the power of mathematics and of quantitative thinking in understanding the natural world. Then, third, we're going to explore some of the implications of special relativity. And finally, I'll touch on the much more complex subject of general relativity, which deals with accelerating reference frames. Maxwell's equations, they claim that the speed of light is a universal constant, 186,000 miles per second, for every observer in the universe, so long as that speed of light is measured in a vacuum. But this statement leads to a stunning paradox. In our everyday experience, velocities are additive. Imagine you're standing on a train, and the train's traveling 100 miles per hour. If you then take a baseball and throw it forward at 50 miles an hour, that baseball is going to travel at 100 plus 50, or 150 miles per hour. By the same token, if you turn around and throw the baseball backwards at 50 miles per hour, then to an observer on the ground, while the train's traveling 100 miles per hour, the ball is traveling 100 minus 50, or just 50 miles per hour. The situation that you see the ball traveling at one speed and the person on the ground sees it traveling at a different speed has to do with your frame of reference. If you're in a moving frame of reference relative to somebody else, then your measured velocities are going to be different. Another classic example of these ideas of frames of reference occurs if you're traveling in a car and you toss a ball or flip a coin into the air. As far as you're concerned, that object just goes up and comes down in your hand in a straight line. But someone looking from the side would see that ball or that coin adopt a curving path as you move forward, a parabolic path. Again, the different description of these two kinds of motion has to do with the observer's frame of reference. You might argue that the frame of reference of the person standing on the solid ground is the correct frame of reference. The person moving in a car or in a train, that's a moving frame of reference, which is less special, it's less significant. But then think about the point of view of a space traveler who's sitting out at stationary position in space looking at the Earth's orbiting around the sun, the Earth's rotating on its axis, and here you are in your stationary Earth, but you're undergoing all these complex circular motions at the same time. So what is the proper frame of reference? And most physicists would argue that all frames of reference are equal in the sense that you can use them to determine the natural laws, and those natural laws should be the same. But this leads to a stunning paradox. Think about the behavior of light. If I stand someplace and shine a flashlight, that light's traveling towards you at 186,000 miles per second. Now, according to Maxwell, if I were on a speeding spaceship, if I were traveling 100,000 miles per second myself and traveling towards you, and still shone that flashlight at you, you would measure the speed of light at 186,000 miles per second. Because that's built into Maxwell's equation. That's the speed of light is a constant. It doesn't matter whether the object is moving towards you or away from you or whatever. That's the speed of light. So according to Maxwell's equation, the velocity of light is not additive. It's an absolute constant. And this brings us to one of the towering figures in the history of science, Albert Einstein, who tried to come to grips with this crazy paradox. How could the speed of light be constant, even for an object traveling towards you or away from you at near the speed of light? So much has been written about Albert Einstein. It's hard to get a real grip on the person. He was a brilliant and reclusive thinker, a reluctant public figure, a passionate advocate for social justice. He was a failed husband, a disappointed father. It's really hard to know who this man really was, this isolated genius. He stood apart from the rest of the people in his time, it seems. He was born in 1879 in southern German town of Ulm. As a young student, he developed an intense dislike for the rigid public education system. He showed little enthusiasm for learning until his uncle began to teach him mathematics on the side. The teenage Einstein excelled in science and in math, and he was admitted to the Swiss Federal Polytechnic School in Zurich to train as a teacher. He wanted to become a teacher. Even in college, he tended to avoid classes. He thought they were dull and pedantic. He didn't like the lecturers, and he studied primarily on his own. Einstein graduated with a degree, and he also gained Swiss citizenship in 1900. He then continued on to get his doctorate from the University of Zurich in 1905. Upon graduating, Einstein was unable to find a teaching position. He was quite disappointed in this. In fact, it turns out it may have been one of the great lucky breaks in the history of science, because instead of teaching, he took up a job as a technical patent examiner in Bern. And that was a position that left him plenty of time to think and to write, to do the sort of thing that Isaac Newton did when he was a young man. In one astonishing year of 1905, Einstein published 4 transforming papers. These papers include the special theory of relativity, the understanding of the equivalence of mass and energy, that is E equals mc squared. And I'm going to talk about these 2 papers in the context of this present lecture. Then he presented a theory of Brownian motion, which provided compelling evidence for the existence of atoms. I'll talk about that in the next lecture. And finally, he described the photoelectric phenomenon in terms of the quantum theory of light. That was a major paper in the development of quantum mechanics, and you'll have to wait till lecture 19 to hear about that discovery. Einstein had an amazing year, just like Newton did back in 1665 and 1666. These discoveries seem to be in esoteric aspects of theoretical physics, but they brought Einstein a huge amount of fame and a succession of professorships at Zurich and at Prague and in Berlin. In 1916, it saw the publication of his general theory of relativity, and he won the 1921 Physics Nobel Prize for his photoelectric law and also for work, quote, in the domain of theoretical physics. They weren't quite ready to acknowledge the theory of relativity as his great discovery, so they gave it to him for something else that was certainly profoundly important, but not what he's best remembered for. From that time, 1921, until his death in 1953, Einstein became an increasingly public figure. He happened to be lecturing in California when Hitler came to power, and he stayed in the U.S., accepting a position at the Advanced Studies Institute in Princeton, New Jersey. He became an American citizen in 1941. Einstein's public role was quite important. He played a significant role in the history of the atom bomb. For example, in 1939, he wrote a letter to President Franklin Roosevelt warning that the Germans might actually be constructing or attempting to construct an atomic bomb, and the U.S. might want to consider doing a similar sort of program. The Germans, it turned out, did not have a major nuclear weapons program, but Einstein's letter turned out to be a prime impetus for the Manhattan Project. He was a passionate supporter of the Jewish state and was even offered the presidency of Israel in 1952, although he turned down that position. What an amazing resume this was. It's difficult to get a sense of this man. His friends spoke of Einstein as a person with warm humor. He loved to sail. He had passion for music. But I suspect that Albert Einstein's always going to remain a mythic figure in the minds of most people, somehow outside of the realm of the normal sort of everyday people that we meet. His mind was simply beyond understanding for most of us. Well, let's return to this light paradox, the one that Albert Einstein attempted to solve. If light speed is constant, then velocities are not always additive. What are the consequences of that idea? Einstein thought deeply about this situation, and he realized that there are really only 3 possible ways to resolve the dilemma. On the one hand, you could say that the laws of nature are different in different frames of references, so that a different version of Maxwell's equation is required in different situations. If you're traveling fast, you need one version of the law. If you're traveling slower, you need a different version of the law. If you're on Jupiter or if you're in the middle of deep space, you might need a different set of laws altogether. That's possible. But Einstein, like most other scientists, just rejected this idea on philosophical grounds. It would be extremely difficult to test experimentally, for one thing, because you can't really set up a laboratory in some distant place in space. And just the idea that the physical laws would somehow be different in different parts of the universe didn't ring true to science. To scientists, the universe has a symmetry, it has an order, a predictability, and that must be part of it, that the natural laws are the same everywhere. And then again, there was the possibility that Maxwell's equations could be wrong. Perhaps the speed of light is additive in a normal way, and that the equations of Maxwell just don't take into account this property of light. Einstein and his contemporaries were quite reluctant, however, to accept this idea because everything else about Maxwell's equations described electricity and magnetism so perfectly. It seemed to be a complete and thorough framework, mathematical framework, and so why should light violate that framework? And then there's the third possibility. Our common sense about the way velocities add could be wrong. Our everyday experience doesn't deal with objects traveling 186,000 miles per second. We can't perceive that kind of velocity. And so we don't have any everyday experience, and so maybe our intuition is just plain wrong. And Einstein chose to accept this third case, but when he did, he found out that the consequences are quite bizarre. The principle of relativity states that laws of nature, Newton's laws of motion and gravity, the laws of electricity and magnetism, the laws of thermodynamics, all of those laws are the same in every possible reference frame. So Einstein's theory of relativity begins with this assumption and considers logical consequences of light having the same speed in all different reference frames. The first part of the theory of relativity was published in 1905. That's special relativity, and it deals with reference frames that are not accelerating, that are in uniform motion. Remember, Newton divided all motion into uniform and accelerating motion. And then you had the general relativity, published much later, 1916, mathematically much more complex, and that dealt with accelerating reference frames. Here's the story about how Einstein began thinking about light and relativity. He was riding on a trolley car in Bern, Switzerland, and he looked out the window at a clock tower. And just as that clock tower was about to strike noon, he imagined what would happen if the trolley car sped up to almost the speed of light, or even to the speed of light. Here's what he said would happen. He would be surfing on a wave of electromagnetic radiation coming from that clock. He'd have a pocket watch, and it would be ticking away seconds normally. Tick, tock, tick, tock, tick, tock. But the clock from which he was receding at the speed of light, he'd be riding the crest of the wave that carried the information that it was 12 noon. And as long as he watched that clock, the clock wouldn't be ticking. The clock would have appeared to stop, because the information that it's 12 noon is traveling away from the clock at the same speed that you're traveling away from the clock. The astonishing conclusion is that the measurement of time, just like the measurement of motion, is relative to the observer's frame of reference. So what I perceive as the passage of a second, or a minute, or an hour, or a day, might be quite different from what you perceive as the passage, if we're traveling at very different velocities. We can quantify this idea by the analysis of what's called a light clock. And this is one of Einstein's great conceptual breakthroughs, the analysis of exactly how much time slows down when you're traveling fast. A light clock incorporates a light that flashes on and off, and you have to have a sensor and a mirror, a pair of mirrors, in fact. What you do is you have a mirror that reflects the pulse of light. The light triggers, it flashes on, the light pulse travels up to the mirror, it bounces back and is detected by the sensor, which then triggers the light again. The light goes on, bounces, it sends a pulse of light up to the mirror, the light reflects back, is sensed by the sensor, and so you get tick, tock, as the light goes back and forth. Pulse of light bounces off pulse of light. And you can imagine, you could, for example, set up a light clock that was 186,000 miles long, and that clock would have a tick and a tock, 1 second, 2 seconds, 1 second, 2 seconds, because light travels 186,000 miles per second. So if you're standing on the light clock, you just see seconds ticking away normally. But now imagine if that clock is moving relative to you. You see it moving laterally at some high velocity, for example. In that case, you see the light pulse do the following thing. The light pulse leaves, the light flashes, and the light has to adopt an angular path, and then the light goes on an angular path again, angular path. The path that the light is traveling as you observe it is much longer. And because the path is longer, it's not just 186,000 miles, for example, it may be twice that long. The clock appears to slow down because the light has to be traveling 186,000 miles per second. That's how fast you see the light traveling, and yet it appears to have to travel a farther distance. The person standing on the clock just sees tick-tock, tick-tock, tick-tock. You see tick-tock, tick-tock. And the slower, the faster the clock goes relative to you, the slower it appears to be ticking. You can calculate the exact amount of time dilation just using simple geometrical arguments, because the angle and the distance involved in that path of light is just related to the speed that the clock is traveling. Indeed, Einstein did this calculation, and it turns out that every time your pocket watch ticks 1 second, the light clock moving at a velocity of v takes only a fraction of a second, and that fraction of a second can be given by a simple equation called the Lorentz equation. The equation says that the time, which is some fraction less than 1, equal to or less than 1, is the square root of 1 minus the quantity v over c squared. Now let's think about this equation in a little more detail. V is the velocity in which you observe the clock moving. C is the speed of light. If v is 0, you have 1 minus 0 over c squared, or the square root of 1. So the time that you see is the same as the ticking of the clock. It's just the same. But any time velocity is greater than 0, the fraction v over c is going to be greater than 0, and v over c squared is also going to be greater than 0. So 1 minus that quantity is always going to be a little bit less than 1. You take the square root of that, so you have a fraction which is somewhat less than 1. You can calculate the various Lorentz factors for different velocities. And for those of you listening on audio tape, there's a table of these in your booklet, just to give you a sense of how this Lorentz factor varies with different velocities. For example, if you're traveling 1 mile per second, the Lorentz factor is not 1, it is 0.99999999997. If you're traveling at 1,000 miles per second, which is still much less than 1% of the speed of light, the Lorentz factor is 0.99997. If you're getting up, though, to near light speed, for example, if you're going 100,000 miles per second compared to light speed, which is 186,000 miles per second, the Lorentz factor is 0.71. And when you get all the way up to 180,000 miles per second, you're traveling at greater than 90% of light speed, then the Lorentz factor is 0.063. So time appears to have slowed way down. It's only a 20th as long. This table, this list of Lorentz factors, suggests that relativistic effects are barely noticeable at velocities below about, say, 10,000 miles per second. You really wouldn't be able to measure them in any straightforward laboratory way. The only situations where the extreme relative velocities are important are in cosmic rays, for example, cosmic rays streaming to us from other stars. And those are the only cases where we actually see these coming in nature, very high velocity particles. We also create these very high velocities in particle accelerators. And believe it or not, when you operate a particle accelerator, you do have to worry about these relativistic effects. You get electrons, for example, going around in a ring at relativistic speeds, and so the time experienced by those electrons changes relative to your frame of reference, and you have to correct for those in all your calculations. According to these calculations, if the relative velocity of an object ever actually reached 186,000 miles per second, then the Lorentz factor is going to be 0, because you're saying 186,000 over 186,000, which is 1. 1 minus 1 is 0, and so time stops. This is the situation Einstein envisioned in that trolley car in Switzerland. Time dilation really is of little concern today, except, as I said, for the people who operate those particle accelerators. But imagine a future society in which high-speed space travel is commonplace. In that case, time dilation could wreak havoc with people's lives. Imagine that you board a spaceship, it accelerates to 180,000 miles per second, heads to a nearby star, you take maybe a year to get there or some period of time. 10 years later, according to your watch, you return to Earth. So by your watch, you've experienced 10 years, you're 10 years older, you've had 10 years worth of experiences, probably great experiences. Going to a nearby star must be really neat. You know, you see lots of things you never imagined seeing before. You come back to Earth, you want to tell your family and friends. What you found is that you've experienced that 10-year journey, but on Earth, 160 years have passed. Your earthbound family has long since died, along with your grandchildren, along with your great-grandchildren, everyone you knew. In a future society such as this, and with space traveling at near light speed, you can imagine generations leapfrogging each other. It would wreak havoc with genealogies, if you can imagine what that would be like. Special relativity has other strange and very unexpected consequences as well. Let me take a few minutes to review some of these consequences. Very paradoxical results you'll see. Moving yardsticks, for example, appear shorter than stationary ones. The fractional shortening is exactly equal to the Lorentz factor. So if you saw a yardstick moving out in space, as it got near the speed of light, the yardstick, as you measured it, would get shorter and shorter and shorter. And the real paradox is when you got to the speed of light, the yardstick would appear to shrink to zero, at least if it's moving laterally to you. This effect is also observed in particle accelerators when you have a bunch of electrons that are moving around a ring. As you go to higher and higher speed, the distance that separates that bunch of electrons gets shorter and shorter, and that's the relativistic shortening that we can actually measure in a laboratory. Mass also depends on velocity, it turns out. The greater the relative velocity, the greater the mass of the object. And here again, the increase in mass is inversely proportional to the Lorentz factor. So here's a case that if you saw a mass out in space, as it gets closer and closer to the speed of light, it appears to become more and more massive. It appears to have more and more gravitational attraction, for example. And if you ever could get the situation where a mass was accelerated to the speed of light, it would have infinite mass. This is the reason, because remember, an object's mass is defined as the resistance to being accelerated by a force. That's one of the definitions. And since you'd have to have an infinite force to accelerate an infinitely massive object. So that's why you can never accelerate a massive, any sort of mass, an electron or a proton, atoms, anything. You can never accelerate them to the speed of light because it would take an infinite force to do it. And this is why this theory of special relativity forbids any mass being accelerated to the speed of light. You can get close to it, but as you get closer and closer, it takes more and more force to do that acceleration. There's a remarkable consequence here. At least mathematically, this means that any object traveling faster than light speed, and nothing prevents this at all in Einstein's formulation, that object can never decelerate to below light speed. So there's sort of a barrier here. You can't actually have objects traveling faster than the speed of light, or they can travel slower. They just can't travel at the speed of light, according to these equations. Now, the equations may not model all situations in the universe, but they seem to work pretty well. So that's an interesting consequence of Einstein's law. So far, we've seen that if light speed is constant in all reference frames, the consequence is that time and length and mass have to be relative. A few months after formulating these remarkable ideas, Einstein realized another profound implication of his special relativity theory that he hadn't thought about at first. The first law of thermodynamics has to apply to every reference frame. The total amount of energy has to be constant. But since mass increases with velocity, and the total amount of kinetic energy, that's mass times velocity squared, can't follow the energy conservation law in this case. So something weird has to be going on. And so Einstein realized there has to be an equivalence then of mass and energy. He wrote this short revolutionary paper explaining the paradox, and he prepared that equation, E equals mc squared. There has to be an equivalence of mass and energy. Energy equals mass times the speed of light squared. And that's the rest energy that corresponds to your mass. We now know that a few pounds of nuclear fuel can provide electricity for an entire city. A basketball-sized nuclear weapon can destroy one in an instant. Einstein's theory of special relativity, dealing as it does with reference frames in uniform motion, it's a fairly straightforward process in algebra. You could understand that if you look at our textbook, The Sciences. You'll see we actually derive the Lorentz factor in that book. It's a fairly straightforward process of algebra. But general relativity, which deals with accelerating reference frames, is a different matter. It provides all sorts of new perspectives on forces in nature, and yet to actually go through the whole process of understanding it, it's extremely difficult. But let's consider just a simple thought experiment, another experiment that might help you understand where this idea came from. If you were in a sealed, windowless room on a spaceship that was accelerating in exactly 1g, that's the acceleration of gravity at the Earth's surface, is there any way that you could tell that you were in a spaceship as opposed to being just on the surface of the Earth, being pulled down by the Earth's gravitational force? The answer, Einstein concluded, is absolutely not. That the acceleration due to gravity at the Earth's surface feels exactly as it would in deep space if you were in a rocket ship that was accelerating at 1g. No way to tell those two apart. Gravitational forces and acceleration, then, are somehow equivalent, and this is a very deep distinction. There's an arbitrariness to whether you call gravity an acceleration or a force. Newton saw the connection in his laws of motion. He said force equals mass times acceleration, so mass becomes the scaling factor between the force and the acceleration. But Einstein explored the universal equivalent from a relativistic point of view. Newton thought of the universe as a flat surface. Balls roll in a straight line and at a constant velocity unless acted upon by a force. Newton would say that the moon follows a curved path around the Earth because of that gravitational force. But Einstein had a new way of thinking about the universe. He saw the universe as being a series of warped surfaces, and mass warps that surface. So balls follow contours along this warped surface. An object in orbit, therefore, is following the contour around one of the deep gravitational wells. The ultimate test of any theory is whether or not it makes useful predictions. And it's not easy to detect most relativistic effects, but there are a few specific ways in which the predictions of Newton and Einstein differ from each other, and you can use these to test whether Einstein was right. According to Newton, light should follow the warping of space and thus bend. That's according to Einstein, that Einstein said if you have a very heavy mass, that light would actually bend as a result of the gravitational force because it follows that warping of space. Newton would say light travels in a straight line. When people did experiments, when they saw light coming from a distant object passing a galaxy or passing a star, they actually were able to measure that bending of light. The exact shape of orbits differ slightly in the Newtonian and in the Einsteinian formulations. Meticulous observations show that Einstein's model works better than Newton's when you make very precise and accurate measurements. Also, Einstein predicts that the frequency, that is the color of light shining upward in a gravitational field, should decrease slightly, while light shining down in a gravitational field should increase in frequency slightly because gravity affects light and it affects its wavelength. These predictions have also been demonstrated quite clearly using lasers. Now, these observations don't mean that Newton was wrong. It doesn't mean that his laws of motion should be abandoned. What it means is that Newton's laws work extremely well for low velocities, for everyday sorts of situations that we all experience. But when you start going to relativistic velocities where none of us have ever experienced these sorts of effects, you need a new set, a more inclusive law that incorporates Newton's laws and goes beyond it. Goes beyond it because you can apply that Lorentz factor. Let me summarize this wild ride through the theory of relativity. I know this is a lot of crazy stuff, but it's part of our physical world, and it's an amazing part of living in this century. The central idea of relativity is that every observer sees exactly the same natural laws, including the laws of electromagnetism. This means that there's a constant speed of light, and Einstein used that idea to get the special relativity theory and its great central paradox. The time and space are relative to an observer's reference frame. Fast-moving clocks tick slower than slow-moving clocks. Among the amazing paradoxes of this work are that length and the length contraction of objects, the fact that mass increases as you approach the speed of light, also the equivalence of mass and energy. Finally, we saw that general relativity deals with that complex case of accelerating reference frames. In the next lecture, we're going to continue our foray into the physical realms beyond our everyday experience when I introduce matter at the scale of the atom.